Like it is a heterogeneous group.
Okay, okay, okay.
Right, huh? Okay, okay. Wait, we'll wait. Thank you.
వాట్సాప్ లింక్ రాలేదు శ్వేత. పడట్లా పడింది మ్యూటింగ్
Yes, good evening, everyone.
ఈవినింగ్ సార్
Dr. Sushil, sir.
గుడ్ ఈవినింగ్ సార్
Yeah, good evening, everyone.
Yes,
And
sir.
I
Yes, sir.
welcoming
I'm
you
here
all.
only.
I welcoming you all, the participants and the invited speaker, Dr. Sushil Kumar Sarkarji, and my teachers, faculty from Andhra University. Welcome you all for the final session of today's workshop. Uh, Just I want to read a small, very, very small, because Dr. Sarkarji has given very, very small biodata. I know him, he's very close to me, he's a friend of mine for the last 15 years. Dr. Sushil Kumar Sarkar is working as a senior scientist in the prestigious Indian Agricultural Statistical Research Institute, ICAR, New Delhi. He has a specialization in the design of experiments, and his interests are in multivariate techniques, statistical genetics, and he published more than 70 research papers. And he, in one edited book also, he completed. And right now, he is holding the charge, the position as a joint secretary to Indian Society of Agricultural Statistics, which is publishing the Journal of Agricultural Statistics by IASRI. Uh, first of all, I want to thank Dr. Sushil Kumar Sarkarji for accepting my request within a short notice, and he has taken a very complicated topic, multivariate. So far, we have discussed univariate, but he is going to discuss with multivariate techniques. He has given only 1.5 hour time. Of course, it is very short time to complete to cover multivariate techniques. But within the time, I think he may cover a maximum possible. And the codes and slides are just now we share to all the registered participants. And one more request. Please mute your audio because it is disturbing the speaker. It is disturbing the speaker. That's why I'm requesting you, everyone, please mute your audio so that he can deliver his talk. And whenever you have any doubts or thing, we can give the last 10 minutes, we can discuss and he will clarify the doubts. So, with these few words, I request Dr. Sushil Kumar Sarkarji, please start your session on multivariate techniques.
Thank you, sir,
Thank
for
you.
your very kind words. And it's indeed a pleasure and feel honored to speak to as such a occasion when respected Dr. Rao is going to retire. And indeed, it's a pleasure for me and an honor. And very good evening to the participants. I will deliver 2 3 topics I have chosen. I'll give you a data set for practice also. At the interval of every 5 to 10 minutes, I'll ask if there is any clarification needed. Because if I keep on going and don't give you a time to ask, you will miss many things which in between we need to clarify. So after the interval of 5 or 10 minutes each, I'll ask if there any question. So I'm sharing my PPT and I have chosen very, so it's visible. My PPT is
Yes,
visible
it is
Yes,
visible.
and
sir.
Yes,
I'm audible hopefully.
yes, very
Okay,
clearly.
thank you, sir. Clear and loud. Okay, so for today's talk, I have chosen first multivariate analysis of variance. This we generally do, and then I have chosen principal component analysis. For if time permits, I'll go to discriminant analysis also. So what we do, whenever we collect some data from different groups. So, sir, Rao sir, VS Rao sir, Dr. Rao. Okay. So what we do, we generally compare the arithmetic means. And how we compute arithmetic mean? It is the sum of all the observations divided by number of observations. And when there is only two groups, we use t-test. And when there is more than two groups, we use analysis of variance technique. Suppose we have three groups, okay, and we want to test three different t-tests. Should we go for three different t-tests? Yes or no? Anybody? If we have three groups, A, B, C, three groups are there. We want to compare their means. Can I apply three different t-tests?
No, sir.
And uh,
No, sir.
why?
Because t-test studies for small sample for a single and it is for two samples.
Yes. So
Yeah,
I want to
difference
go
of
for different see A is equal to B, A is equal to C, and B is equal to C. But we
then
should
we'll go
not
for
go.
analysis. Then we'll go for analysis of variances.
Yes, you are all right. But what was the logic behind that? That I wanted to tell you. Do you know the logic? Why should we go for ANOVA, not for three different t-tests?
Because we have to find the significance between means.
You are right. When we go for three different t-tests, actually we will increase our level of significance, that is alpha.
Yeah,
Okay.
alpha.
If you
Yeah.
go for different three t-test, 0.95 into 0.95 into 0.955 is 5% level of significance is there. Actually, you are going to deal with your alpha will be 15%, not 5%. Okay.
What is the reason, sir?
I told you, na, if you
Yeah,
have, yeah, 5%
yeah,
level of significance, okay,
mm,
then 0.95 into 0.95 into 0.95, you multiply three times, it will become 0.85 like that. So actual alpha will be 15%. If you want to understand, let me tell you one example. If you are rolling a dice, okay, die. So how many faces are there? There are six faces. Suppose you
yeah,
want six, okay, and you are tossing a coin. You want a head. What is the probability? 1/2, right?
yeah, yeah,
If I toss a coin and roll a die and I want the combination h and 6, the probability will be 1/2 into 1/6, 1/12, isn't it? So
yeah.
two independent events, when we want to occur simultaneously, we multiply their probabilities. Like that here also, if 0.95 is the probability of occurrence, means alpha is 5%. So 0.95 into 0.95 into 0.95, the alpha will become, sorry, the probability of success will become 85% and failure 15%. That's why we should not go for different 3T tests. That I always wanted to tell every student, if you have more than one group, don't go for different T tests, go for ANOVA.
That.
Yeah.
Thank you, sir.
Second thing, we can do many analysis using software R, SAS, SPSS, no problem. We must understand the logic behind it. How do it get? So we have read about the partitioning of sum of squares. Okay, with a very simple example, I would like to tell you that suppose in group 1, 1, 2, 3, there are three observation, and in group 2 there is 5, 6, 7, three observation. If I take the mean of these, this is the 2, and the mean of group 2 is 6. Now the sum of squares. Sum of squares means observation minus mean and its square. Okay. So 2 here, the first one is the 2. 2 minus 2 is 0. 3 minus 2 is 1 and its square is 1. 1 minus 2 is minus 1 and its square is 1. So this sum of square is 2. Same as here, if you calculate, it will become 2. Now, sorry, got an urgent call. Uh, I should keep on, don't disturb. Yes. So now the overall mean is 4. So this total sum of square comes like 2 minus 4 and its square is 4. 3 minus 4 is 1. Sorry, minus 1 and its square is 1. So 4 plus 1 is 5. And 1 minus 4 is minus 3 and its square is 9. So it becomes 14. 4 plus 1 plus 9. Same here. So this will become 28. And now you see, so the total sum of square is 28, and the within sum of square is 2 plus 2 is 4. Okay. So here when we write in ANOVA, we write error 4, effect 28, and total is 24 and total is 28. That's how partitioning of sum of square happens. When you have more than two groups, so you will deal with each of the mean and that correspondingly give you sum of squares. Okay. Now, hurriedly, I would like to come to Manova. Why Manova? So when should we go for Manova? When we collect more than one observation on a subject. Okay. Suppose we are taking a plant and we are taking many characters from that which are correlated among themselves. If this is the condition, we should go for the multivariate analysis of variance. Here I have written that if we go for different ANOVA for different characters, same logic, your level of significance will increase. So here I have written, if we have 8 characters and we go for 8 different analysis of variance, we actually deal with 40% of level of significance. Okay. That's why if we have more than one observation from on each object, we must go with multivariate analysis of variance. Any question, please? I could hear some voice. No. Thanks. Now, another reason to go for Manova, none of the individual ANOVA may produce a significant main effect on dependent variables, but in combination they might be. Here, the intercorrelation of the dependent variables play the role. We will understand through one examples. There are there are some assumptions. All the dependent variables must be distributed normally, as there are assumptions in ANOVA also. Any linear combination of dependent variable must be distributed normally, and homogeneity of variance covariance matrix. Okay. So what do we mean by homogeneity of variance covariance? What do we mean by homogeneity of variances? Do they come same or what? They are not same, but given a range, when we test using F test or Bartlett chi-square test, they should not come significantly different. So that we call homogeneity of variances, right? So in univariate, we use t-test ANOVA. In multivariate, if there is two samples, we use Hotling's t-square, and if more than two characters, we use multivariate analysis of variance. Now, let us see how it goes. When we have, suppose, one character, we have one observation from each object. We have mu1 is equal to mu2 is equal to mu3 and up to mu z if g is the number of groups. But in multivariate analysis of variance, we deal with the vector. So here the first letter mu11. So mu1 is representing the first group, and this one is second one is representing the character. So mu21 means we are dealing with the second group, character 1. So mu represents the mean of that group. So these are, we have p number of observations from each object. So that's why we can write mu1p. It means from first group, this is the mean of pth character. Okay, pth observation. Likewise, mu21 is representing the second group, second sample. Okay. Likewise, here we have G number of groups and P number of characters. So, our Y will be N into P matrix. The test statistics for multivariate linear models are Wilks lambda, Pillai's trace, Hotling-Lolly trace, and Roy's maximum root. Now, when we have a matrix and we compute the eigenvalues, what does they give us? If we sum all the eigenvalues, it becomes the variance. Okay, that's why in all the statistics you see in Wilks lambda, this is some this pi I is equal to 1 to j, it is showing the multiplication of 1 upon 1 plus lambda I. So this is representing lambda 1 means first eigenvalue, lambda 2 means second eigenvalue, and like that. So you see all the test statistics are involving eigenvalues. So let's see this example. This is factor 1 and this is factor 2. This is the low level of factor 1 and this is higher level of factor 1. This is low level of factor 2 and this is high level of factor 2. How many dependent observations are there? Y1, Y2, Y3. There are three characters, right? So, what will be our first null hypothesis? There is no factor 1 effect. Mean to say the level of low and high are equal. So, when we set our data like this and we compute the mean of y1, y2, y3 of factor 1 at low level, this is 6.49, 9.57, 3.79. So you can see I have written here the vector, and for second level that we denote as high, this is the means. So what we actually want to test here, equality of these two vectors. Earlier when we go for ANOVA, we test for the equality of two means. Here, the vector of means of the number of characters more than one. Now, second null hypothesis will be there is no factor 2 effect. Okay. The mean of low level of factor 2 is equal to mean of high level of factor 2. So here we can see 6.59, 9.14, 3.44 are the mean of these levels. These are three, y1, y2, y3 are dependent characters, and 6.98, 9.49 and 4.43 are the mean of these dependent characters. The third null hypothesis here will be there is no interaction effect, means see, we have two factors and these two factor is having two levels. So we can 2 into 2, 4. So there will be 4 combination, factor 1 low, factor 2 also low, factor 1 low, factor 2 at high, factor 1 at high, factor 2 at low, and factor 1 is high and factor 2 is also high. So these 4 treatment combinations will be there. We have calculated their means here. We will be evaluating, examining the equality of these 4 vectors. Any question up to this point?
No, sir.
Okay. So now we will see how we can go, we can do this data in R. So is my R visible?
Yes, sir. Yes.
Yes, okay. So this R is visible.
No, Dr. Sir, it is showing PPT only. Just to move to R.
Okay.
Now, okay. Right.
Now, okay.
Make it a big screen. Right. Thank you.
I think this has become more visible. I have changed to 14, or let's change to more. So comfortably you can see.
Yes, sir.
Yes, yes.
Okay. Mm. Okay, so this is visible. Data 1 is equal to, is it
Yes,
visible?
sir.
Okay, I will not do this. What we will do, I have given you one file, two files basically, Manova 1 and Manova 2. So I will import data. So I will go here in environment and there is written import data set, right? From Excel, I will browse my data and I am taking same example which I was dealing in my PPT. So this is the, here you can see it is written character, character, double, double, double. And here the file name is Manova. If you wish, you can change it. I'm changing it to data 1. So it will come in the name of data 1. Seat. If you have 1, 2 or 3 seats, you can change from here. I have in only one seat. First row as names. I'm having first row as names. So I'm importing it. So I can see this data 1 has been imported. Right? If I run this line, so this is showing me my data. Okay. Now to run Manova, I have to see my factors are F1, F2, Y1, Y2, Y3. Y1, Y2, Y3 are the dependent variables. F1 and F2 are independent variables. So here I will write Y1, comma, Y2, comma, Y3. Okay. And my dependent factor is F1. So I am testing the first null hypothesis. Okay. What was my first null hypothesis? The levels of first factor are equal. So let us run this first line. We get F1 and the p value is 0.002 and so on with double star, and double star means this is significant at 0.01. What should I infer here? What inference can we draw from this? The two levels of factor 1 are significantly different. F2 is having two levels, high and low. So we are testing the equality of low level of factor 2 with high level of factor 2. So again, if we run this line and we see the summary of the result, here we are getting 0.03. So if your alpha is 5%, this is significantly different. If your alpha is 1%, this is not significantly different because this value is less than 0.05, but this value is more than 0.01. So this is see, this is star. This is saying this is significant at 5% level. If it earlier it was significant at 1% level also. That's why there is 2 star, right? If we write F1 and we put a star, or first let me put a colon. So I am giving the interaction. Now it will test all the 4 treatment combinations and give you the result. See, this is the interaction. And if I put a star here, and run this. Now you can see the difference. So here factor 1, the levels of factor 1 having 3 dependent variables are significantly different from each other at even 1% level of significance. For factor 2, this is significantly different at 5% level of significance. But the interaction, this is not significant. Any question up to this point?
Can you explain
I have
what
one
does
question, sir.
Yes, please.
See, not significant means what, sir?
Interaction is not significant. Okay. Have there been a class on ANOVA also, and that to factorial experiments?
Hello?
Yes, sir. Was there any class on factorial experiment also in this workshop? Factorial experiment. No, I think it was not done. What happens here? We are checking the equality of C. This is the first hypothesis that the
Okay, sir.
forget about factor 2 is these two levels means this factor 1 is having two parts low and high, are they
Yes.
significantly different or not? This was the hypothesis. So my ANOVA told with 0.0022 that
Hmm.
these two are significantly different, right? Now
Okay, sir.
again for F2 we tested that, forget about this F1, the two levels of factor 2 that is known as low and high, are they significantly different from each other? My ANOVA with 0.03 is saying at 5% level of significance they are they are significantly different. Now the
Okay.
third hypothesis was that these are the four combination. Okay, factor
Okay, sir.
1 F1 low, F2 low, this is the one combination. Okay, F1 low, F2 high, this is second combination. Third one is F1 high and F2 is high, this is the fourth combination. Okay, third was the
Okay, sir.
F1 is high and F2 is low. So these four combination means these four is it visible now my PPT?
Yes, sir. Yes, sir.
Yes, these four vectors are they significantly different from each other. Now, with the p value with 0.3, it is saying no, these are not significantly different. So this is
Okay.
called interaction effect.
Thank you. Thank you, sir.
So now we have seen up to summary, and here it is giving by default Pillai's trace. Okay, if we wish to compute Hartling-Lollet test, we write summary. This is the name of this result, Manoa result. Manova result, comma test is equal to, we can specify which criteria do we want. So if we run all these, we will find so this is Hotling Lolly test. If we run second one, Roy's greatest root. If we run third one, we will get Pillai's trace. And if we run fourth one, this is the Wilks lambda. This is called Wilks lambda. Now we can see the results. Is there any difference? So here it is 0.0034, here also, here also, here also. No, there is 247, this. Results are almost not exactly similar. There is no change in the results applying 4 criterion. Okay. So what I wish, within 5-7 minutes, you can go through the second Excel table, that is Manova 2, and just run it, see the results. If you have any problem in interpretation or understanding, let me know. You have
Sir,
data with yourself? Yes.
sir, can you please tell me what is the what does the star and the single star and double star represents in the results?
See, here when I put F1 only, it took factor the levels of factor 1 only. When I took factor 2, it took the 2 levels of factor 2 only. But when I put F1 into F2, it is giving the result of F1, F2 and interaction of F1 and F2. Right? So when I need all the results, I will put 1 star F1 into F2. It will give me all the 3 results for F1, for F2 and interaction of F1 and F2. Right, sir?
Okay, sir. Okay, sir. Thank you.
Now, data 1 is the file name. So here I have given data is data 1. So now you import Manova 2, give a name, run it. So you need to change the variable names here. You need to change the independent variables here. Run it and let me know the result or if any difficulty. I have given you Excel file. You can easily import. So would you, yes or no?
Yes, sir. Yes, sir.
If you have system with you, I
Yes, sir.
prefer you should run, otherwise you will not get the feel. I am also doing that.
Sorry to ask, sir. Where is the data, sir? Data 2?
Sir, I have sent one file with the Excel file with the name Manova 2. That is the second example. Okay. Did you get it?
Okay, I will check, sir. I will check. Okay.
Uh, I think VS Rao sir has already sent the R file and data files. Is it with you? Yes or no? Now for the second set, I have to make these changes. Earlier, my dependent dependent variables were y1, y2, y3. Now my dependent variables are number of leaves, leaf length, leaf width, leaf area. My independent variables are treatment and variety. Okay. So I have put my dependent variable here, and after each we need to put separation with comma. Okay. So are you with me on same page? So everywhere I'm giving the name 2, so we should not confuse. So this is the data 2. If I run data 2, so if I select this one, I will get and run it, only this portion, selected portion will run. Okay. And if I put the cursor here and run, the whole line will run. This is my data set stating that there is 10 plus 42 more rows, means 43. Sorry, 22. So 32 plus 10 is 42. Total data lines are 42. Now, here we can see the dependent variable. I have put my dependent variables here, and these are the independent variable. So if we take these 4 characters at a time, it is saying how many treatments do we have? 7 treatments are there. So how to ask the program? See, data 2 dollar treatment and assignment operator write as factor and data 2 dollar TRT.
Eight zero double nine 277 477. చేశారా ఫోను
నగేష్ చేసింది ఎందుకు బుక్ చేద్దాం నెంబరు చెక్ చేసుకుంటాను అంతే
క్యాప్స్
రేపు కొనాలి క్యాప్స్
ఇట్లా రెండు మూడు ఉన్నట్టు
చిన్నవి ఉన్నాయా చిన్నవి ఉన్నాయా చిన్నది
ఆఫీస్ కి అట్లా ఉంటావా
తగ్గించమని అడిగాను పంపించి ఇది బాబాయ్ పెట్టు
Yes, sir. I will get everything, sir.
Yeah, Sarkarji, here only. Yeah, tell me.
Hello, sir.
Pardon? Electricity, oh. Yeah, okay, no problem. Right. We'll wait. Meanwhile, you can discuss any doubts or clarifications.
I think I have resumed. Is it okay?
Yes.
Yeah,
Very
yeah.
nice, very nice. So
Yes.
continue, please.
Yes, sir. I was calculated. Both independent variables are significant, sir.
Okay. So did you get this result from this second data set? Anybody? Did you get result from second data set? Am I audible?
Yes, sir.
Okay, thank you very
Sir,
much.
yes, sir.
So did you get result?
Yes, sir. Yes, sir.
So is result similar to mine?
Both independent
Like
variables are
this?
significant.
Yeah.
Yes, like
P
this.
values are very, very less. See,
Yeah.
2.2 and then this is minus
Yes,
15.
exactly, sir.
Yeah.
Exactly, sir.
So both the factors are
Independent
significant. Means
significant.
how many varieties have been there?
What, sir?
How many varieties have been there? There have been two, avocado and red alert. Okay. And there were 7
Okay, sir.
treatments, T1, T2, T3, T4, T5, T6, T7. But as in Innova, we do post hoc analysis. Okay. It is not available in multivariate. There we get the T grouping of T1, T2, T3. Okay. Here that facility is not available till date, as far as I know. So should we move for second one, that is principal component analysis?
Yes, sir. Okay, sir.
Okay. What actually we do, we plan for principal component analysis. When we have a large number of variables. Suppose we have a large number of independent variables and we have few observations that are less than the number of independent variables. If your independent variables are suppose 20 and your observations are 10, okay, in that case we cannot estimate all these effects. Or when these variables are correlated among themselves, then we use principal component analysis. When the dependent variables are correlated, this is called problem of multicollinearity. Okay, and when there is problem of multicollinearity, the regression estimates are inflated. Okay, so what we get, beta 0, beta 1, these coefficient that are inflated and their variance 2, so we don't get the real picture. So in that situation, when the large number of variables are there and they are correlated to each other, we go for principal component analysis. And what we do, suppose earlier we had 20 number of independent variables, we come out with few numbers of suppose 2 or 3 variables, new variables, which deal with maximum possible variance within that, and these we for further analysis we can go with these new variables. Now these new variables are, this have already told you, so these new variables are linear combination of your original variable. So suppose x1, x2, x3 up to x20, you have 20 independent variables. We will make another variable z1 is equal to a11 x1 plus a12 x2 plus a13 x3 and so on a120 x20. Likewise, we will make second new variable z2 is equal to a21 into x1 plus a22 x2 up to a220 x20, and these are the linear combination. Now the beauty of these coefficients a11, a12, a120 or a21, a22, a220 are that if we square these values and sum it up, it will become 1. Okay, so for any of the z1, z2, z3, we square the values of coefficient and add them, this will become 1. So it ensures that variance is not inflated, variance remains same. And these a11, a12, they are nothing but the values of eigenvectors. Okay, and we deal with here eigenvalues and eigenvector. So whenever we deal with the multivariate analysis, we always deal with the eigenvalues and eigenvectors, right? So we make new variables which are the linear combinations of the old original variables. Any question up to this point? Why to use PCA? Why to go for PCA? How new components are calculated? Any question up to this point?
No, sir. No, sir.
Yes, please. No question. Okay. We generally, I have seen many of the papers, they go for principal component analysis. That's why I thought that I'll deal with this. So what we do, we create new variables that are the linear combination of your old variables, and we do this in such a manner that the coefficients follow some properties. If we square each of the coefficient and add it up, it will become 1. Now, let's do it in practical way. So, I am taking this data. Here, my PP is plant population, pH is plant height, NGL number of green leaves, and yield. Now, one thing to understand, this is not regression. Here, we are dealing only with independent variables. There is no dependent variable like that. So, this is not regression. We are just converting the our original variables to some new variables that will follow some property. So, these are the observations, and I'm opening my R file. I have already sent you the data.
Yes, sir.
There is some sound from one computer icon. So these are PP, pH, number of green leaves, and yield. So this data set name is PCA. The data 1 was for the Manova 1. For second set of data, we put data 2. Now this I have given the name PCA. So only few lines and you will get the result. But let me tell you, we will use one function called printcomp here. This PCA is the name of data set. Now here we are putting COR that
Sir, not
represents.
visible, sir.
Huh?
Sorry to interrupt, sir. Not visible that data, sir. In our console, not visible anything, sir.
Not visible.
Yes, sir.
Just a minute.
It's fully dark, sir. The console is
Yes, now it is
fully
visible.
dark.
Yeah.
There is no
Now
font.
it's visible.
Yes, sir. Yes, sir. Now it is visible.
Okay. So what do we get from principal component analysis for our understanding? Why do we go for principal component analysis at all? Does it give some inference to us? Not at all. We don't get any inference from there. What we do, we just reduce the number of variables to few number of variables. Okay, and the new variables are original variables were correlated. The new variables are independent to each other. It means if we multiply the coefficients of suppose a11, a12, a120 and multiply this with correspondingly a11 with a21, a12 with a22 and a120 with a220, multiply these two vectors and sum of these, it will become 0. Okay, This ensures that these two new variables are independent. We call it orthogonal to each other. It means they are independent to each other. If you compute the correlation, that will come near to zero. I can't say it will be exactly zero, but 0.00 some value may come. Okay. So these new variables will be independent. There will be no correlation. Earlier, the variables would have been high correlation. Now, here, this is the name fit, and this is the function printcomp, which will do principal component analysis for us. This PCA is the name of my data set, and this core 2 correlation is equal to 2. Now, when we deal with principal component analysis, we can go with correlation, we can go with covariance. Now, the question is when to go with covariance and when to go with correlation. Any guesses? Okay. So when we have variance, it is not unitless. Okay. So if your independent variables all are measured on same scale, it is better to go with covariance. If your independent variables are not measured in same scale, what do I mean by same scale? Sorry, I'm not getting good voice. Okay, suppose your x1, x2, x3 up to x20 all are in kg. It's very good. But if your x1 in liter, if your x2 is in kilogram, if your x3 is lumex, like that, you have different measurement scale. Okay, in that case, it is better to use correlation. Why? Because we say correlation is unit free. Am I right? Okay. So when we have different measurement scales, we can go for COR, that is represent the correlation matrix. So we have our data here, PCA, and you all are having this code. Anyone, please?
Sir, yes. Yes, sir. Yes, sir.
Yes, yes. So let's do it.
Yes, already I've done, sir.
You have done?
Yes, sir.
Very good. Now, this line is of importance for us. Okay. Out of total variance, that is 1. This is explaining 45.62% of variation. This component 1. Component 2 is explaining around 23% of variability. Component 2. Component 3 is explaining 16.71% of variability, and component 4 is explaining 14.68% of variability. And if we add up these all four, this will become 1. That we can see here. Component 1 is this percent. Component 1 plus 2 is 68.60. Component with 1, 2, and 3, 85.32%. And all the components together, they are explaining 100% of the variability. So if we don't want to lose any percentage of variability for the further analysis, we have to go with all the four components. Okay. If in original data, the independent variables, if they are not correlated, we will get exactly those in PCA also, because what PCA does, that plays with the variance covariance matrix, and ultimately it goes to correlation and covariance. Okay, so if in original data it is not correlated, we will get same result as the original one. If there is correlation, then only it is beneficial to apply principal component analysis. Now let's see the loadings. Now these are the loadings. Is it visible?
Yes, sir. Yes.
Now what do we mean by these loadings? So it is saying that in principal component 1, and this, what was our PP? Plant population, I think. So this has this much correlation. This yield has this much correlation with component 1. Now you can see this range is -1 to +1, which is the range of our correlation. So this is simply showing the correlation with the old variable with new components. And I told you, if you sum up square, this will become 1. Okay. Now let's plot it and get a beautiful scree plot. Here, just for example, we have taken only 4 independent variables. If you take 20 or like that, this will give you a very good shape of knee type. That's why called as knee diagram. Okay, and when it becomes asymptotic to x-axis, we take only those points. So here around we can take 3. This data is not that much good for, but for just to make you understand, I have taken only 4 independent variable. So this type of graph comes. This is called scree plot. Okay, and then we get the scores. Now, if we go with first 2 variables, okay, if we take and go for the further analysis, we will go with 68.6% of variation explained from the original data. If I take all these 3, component 1, component 2, and component 3, I will be dealing with 85.32% of variability. And if I take all 4, there is the 100% of variability. So generally, what happens if you have a large number of independent variables? First 3 or 4, they explain 92% or 98% like that. So we take only the first 4 and rest we leave, because we can sacrifice 5% variability, and we are getting gain of not including 16 more components. Now, you might have seen this type of graph also. This is called pie plot. Now, if my component 1 is this. So take this line and think it is here. So which one are closer to x1, pp and yield? If we see here, yeah, if we see here in component 1, see the values of pp and YLD. These are the maximum. Here in biplot also, biplot is visible. You see the YLD is more closer to X and PP is a bit further from, if you have a line here 0 to 0. Now for component 2, see minus 0.7. Now if we have line this like this, okay, so this pH is here, and after that number of leaves. So this is how we go for the interpretation of biplot. Please run once, get the result, let me know if there is any difficulty. Now we are getting so many results, but how to save it? How to save these results? You are getting these results, right? But in this window, this you wish to use somewhere. So how to take the results from this window to your workable file? Any idea?
No, sir.
Okay, a very simple code you just see here. Here just write sync, give parenthesis, and in quotes write the name. I'm writing our result dot txt. Okay. Now here I will write SINK and blank parenthesis. I will run all these codes. Now my result would have been saved in my document folder with the name result.txt. But if you have made any workable directory, okay, then this result will go to in your desired place with the name result.txt. So I am sharing my screen, and here I went to my document. Here I find my result. Is it visible to you?
Yes, sir.
Yes, sir.
Yes, yes. And open it. All the results are here which I run in my principal component. It is in Notepad. You can now take it in any format. It's all right.
Yes, sir.
Could you
Yes, sir.
export your result? Now, I would like to tell you few more things. Yes, it's visible, hopefully. Isn't it?
Yes, sir.
Yeah.
Yes.
So,
Yes, sir.
whenever I have run Manova, I have given the result name like sorry, phone calls. Huh? So what I wanted to tell you here, this is the name of my result. Just copy it, paste somewhere here, and put $1. Huh? Now you are getting coefficients, residuals, effect, rank, fitted values, assign, QR, df dot residual, contrast, x level, call, terms, model. You run one by one all these results, because this is saying in the result uh, in the result file, these are the columns available in the result. So you see one by one and get into it. Likewise, if I go to my PCA and write here fit dollar, it will tell me that okay, standard deviation, loading, center, scaling, number of observation, score, call, all these results are available. So whenever you in R, you have a result name, you put $1, you will get all the columns which result has, and see one by one, you will get a good insight of your result, and just learn one by one what these are saying. You will be definitely benefited. Hmm? So you run any of the statistics for the result file, put $1 and see the all the columns will come. Run one by one. Suppose I'm here putting feet and dollar, and then the first one standard deviation. If I run, so I am getting this. These are the standard deviation of component 1, component 2, component 3, component 4. Likewise, you will get many of the result. Just go through it. It's wonderful. So this is what I wanted to tell today. It's almost 8. So I'll wind up. If you have some question, you can ask.
Sir,
Yes, sir.
sir, what is the variable types for doing PCA, sir? PCA variables.
What are the variable types?
Yes, sir.
Now I didn't get. We put here independent variables only. There is no
Uh,
relationship like dependent independent. Okay.
Yes, sir.
So
Like quantitative measures.
yeah, definitely quantitative, not qualitative. It will not take. Ultimately, if you will, you have qualitative data, you have to change into quantitative. Otherwise, how will it calculate? See, this works on a matrix, and matrix needs some digits. Okay, to compute the eigenvalues, eigenvectors. Okay,
Yes.
so it will work only for quantitative.
Okay, so my next question, what is the difference between PCA and factor analysis? These both are looking like same. And what is the rotation doing here, sir? So
Okay,
max
okay,
rotations and all.
okay, 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 okay. You want to understand rotation. Let me tell you first the difference of PCA and factor analysis. Okay.
Yes,
What
sir.
happens?
Yes.
What happens? Factor analysis is one step ahead to PCA, right?
Mm.
So what we do, see in PCA, we are getting components, right?
Yes, sir.
And in components, we can say, okay, in component one, these two factors are contributing more, right? By
Yes, sir.
seeing in the loading.
Yes,
Okay.
sir.
Now you can say, okay, in component 2, these 3 or 4 factors are contributing more. Now you can give a reason for their correlation with factor 1, with component 1, with component 2, with component 3. Okay.
Mm. Yes.
That reason is called a factor. Okay, so that experimenter gives a name to the components. Okay, these three are contributing to this particular factor. These have been the reason. Huh? So what happens if you have the marks of, suppose, social sciences, okay, physics, math, chemistry, and like that, you will find a good correlation in science subject. You will find a good correlation among the, what we call these days, which study, in which arts subject comes.
Arts.
uh, okay, let me say arts. Okay, so you will find so you can say, okay, their reasoning ability here is very good, okay, in this factor, so that's why they are coming in one group. So when your original variables is coming in a particular component, you define it. Oh, this is the reason, this is the factor affecting that, that's why they are together, is called factor analysis.
Oh,
There
okay, sir.
also, there also we use principal component. Okay. Now your
Mm.
next question was, what is the rotation? Is it
Yes,
is
sir.
it is what this was your question? Okay.
Yes, sir.
Uh, let me tell you. Suppose we have x1, x2, right?
Mm. Okay.
Now what we will do? We rotate the axis. Okay, such that the variance. Suppose earlier variance is 40. Hmm?
Oh, okay,
In
sir.
x1 plus x2 variance is 40.
Mm.
We will rotate, and there is a formula sin x1 plus cos x2, like that. Okay,
Okay.
if you rotate the angle of theta, the value of x1 and x2 will change, right?
Oh. Mm. Yes,
A-
sir.
Now what will happen, your x1 will be having, at a optimum point of time, x1 will be having 35 variance and x2 will be having 5 variance. Okay, total
Oh.
variance 40 will not change, but one, after the rotation, your one variable will be explaining more variance. That's called the rotation. After the rotation, what we do, we can leave x2, we can go with x1 only. That's why we do the rotation.
Okay, sir.
I had a good slide
Mm.
for that. If I get here, I can show you. CAP factor. Yeah, I'm having that slide. सर एक लेक्चर में हूँ, थोड़ी देर बाद बात करता हूँ. Just a minute, huh? I am taking that. This I should close. Yeah. The one file is open. That's good. Yes. Yes. Is it visible?
Yes, sir.
Yes. Okay. Now, see what we do in rotation. So these are, suppose x1 and x2, two variables are there. Only I'm taking two for your understanding. And that's why I made this slide. But this time I forgot to show this. So this is the mean. Okay. 8 of x1. And mean corrected means observation minus mean. So this has become this. And this has become this x2, and the variance is 23.09. Here the variance is 21.09. So do you know why this, after this is independent of change of origin and scale? Okay, so this is okay, these values.
Sir.
I have 1 2 3 things to show. Yeah, okay. Now you see, we call it SSCP, sum of squares and cross product. Okay. Now what sum of square? If I square these values and sum it up, it will become 254. Okay. If I square these values and sum it up, it will become 232. And if I correspondingly multiply 8 with 5, 4 with 7, 5 with 3, I will get 181. This is called cross product and this is called sum of square. Okay. Now, if I divide, how many observations do I have? 12. If I divide all these values by 11, I will get this 23.09, 16.45, 16. These two are same. And this is, now what is this? This is variance covariance matrix. And if I divide this value by itself, this value by itself, and this value by the square root of this into this, I will get this. This is nothing but correlation matrix. So from sum of square and cross product, we get the variance covariance matrix, and from variance covariance matrix, we get the correlation matrix. And now what is the rotation? This is the rotation. This is the axis. And if we rotate by theta, so earlier it was the x1 here, okay, and this was the x2, right? If I rotate, my new x1 will be cos theta x1 plus sine theta x2, and my new x2 will be sine theta x1 plus cos theta x2. Now you just see, if we rotate it by 10 degree, okay, my new x1 will be 8.75, my 4 will be 5 point this. Now the variance, earlier it was 23.09, has become 28 point, let me say 66. And if we rotate it by 43.261 degrees, see, out of total variance 44.18, it is 38. Okay. and it is explaining 87.3% of total variability. Here you can see that after rotating 43.261 degrees, this is the value of x1, these are the values of x2. X1 is explaining now out of 44 point something, it is 38.6, and this is 5.6, and that is why we do rotation, that we want to import all the variability to one or few number of variables. We will keep only those variable which are explaining more variance. We will reject those variable now which have become means explaining very less variance, and they are useless for us. That's why we do rotation. Am I clear?
Yes, sir. Yes, sir.
Yeah,
Yes, sir.
that's how rotation goes.
Okay. Thank you, sir. Thank you, sir. Nice explanation, sir. Thank you.
Thank you. So may I stop, sir?
Yes, sir. Yes, yes, sir. Yes, sir.
Yeah, please.
Yes, so nice. And any questions, participants?
I
You want to
I
clarify
didn't
any
try
doubts
make it more
regarding multivariate?
mathematically.
Not only multivariate, he is a master in design of experiments also, because he's working in the design of experiments division now, Dr. Sushil Kumar Sarkarji. So participants, anything already? I mean, the organizers are going to share the feedback form. If you fill that feedback form, the registered participants are going to get the certificate. Okay, so I think after the session, they are going to share to your registered email IDs. You please, all of you, please fill the exact name which you want to print on your certificate so that they can prepare and they will send to online copy. And if no clarifications are required, then anyone, anything, any charts, chart box, here
Okay, sir.
nothing is
So I
there.
will clarified everything, sir. Thank you.
Yeah, okay. Thank you, sir. Thank you. On this occasion, I once again thank Dr. Sushil Kumar Sarkarji, who is my friend, and on behalf of Andhra University, on my own behalf, I am thanking. Before that, I want to get the feedback from the organizing secretary, Dr. Munuswamy, sir. Is there? Yes, now he joined. I think Munuswamy Garu, you want to conclude? You want to give any concluding remarks about the workshop? Muniswam Garu, please unmute.
Yeah, sir.
Yes, yes.
Yes.
Here is our Sushil Kumar Sarkarji from IASRI. Just now he completed the
Yes, sir.
multivariate techniques. You want to say anything as an organizing secretary
sir.
of the national international conference and also the workshop?
Yes, sir. Good evening to one another, sir. So, I am extremely thankful to our resource persons, and also I am thankful to Srinivas Rao, sir. He taken all the sessions chair. So, based on at present, the data science and R, the boom is very high in multinational companies, right? Or data science in big data analytics. So, based on the Srinivas Rao suggested this title, so we incorporated, and he invited all the resource persons. So once again, on behalf of Department of Statistics and Population Research, so mainly we are conducting this workshop and seminar in the honor of Professor K. Srinivas Rao, Department of Statistics. So thank you, sir, for conducting a successfully completion of this 2 days national workshop. Thank you, sir.
Okay, thank you, Dr. Munuswam Garu. So, being the student of the great legendary statistician, Dr. K. Srinivasrao Garu, I have taken this
Yes, sir.
opportunity to conduct and to organize this 2 days, 4 sessions workshop. And I
Yes, sir.
thank all the invited speakers. Dr. Santosh Rathorji, morning he has taken, and forecasting techniques, Dr. Sushil Kumar Sarkarji, who has taken just now completed multivariate, and Dr. M. Ramakrishnan ji. He is from Chennai, who has taken installation of R and the data structures and all he covered. And later, Dr. Akhilesh Kumar Gupta, who is from Bhubaneswar, OUAT, Bhubaneswar. So I must thank all the invited speakers on this occasion, and I also thank all the participants who have interacted and nicely participated without creating any problem to the organizers. So on this occasion, I once again congratulate the organizing secretary, Dr. Muniswamy Garu, the professor and head of the Department of Statistics, Andhra University, and his colleagues, and my teachers, Dr. K. Nirupmadevi Madam and Dr. L. Venkateswara Garu, and the research scholar, Mr. Yogi, who has all the time with us. I must thank and he has helped me to organize this workshop. So again, once again, I thank you, Dr. Sushil Kumar ji. Thank you, and I request all the participants, please fill the feedback form. Thank you. With
Sir,
this,
Umashankar sir is online, sir. Umashankar.
Uma Shankar sir. Okay. So I must.
Umashankar sir is online.
Yeah. Sir, Dr. Uma Shankar sir, do you want to say anything about this today's workshop? Who is a former registrar and he's a senior statistician, great professor. So anyhow, I must thank Dr. Uma Shankar sir also and all the faculty, Dr. Tirupati Rao and all the others who directly or indirectly supported and helped to organize this today's workshop. So with this, I once again thank our Sushil Kumar Karji, and we will wind up the session, sir. Thank you.
Thank you, sir. It was indeed an honor. Thank you very much.
Thank you, sir. Thank you. With this, we will
So,
conclude it. Thank
may I
you.
leave, sir?
Yeah. We are all leaving.
Okay, sir. Thank you.
Thank you.
Sir, we are sending feedback form, sir. Sir, Srinivas sir. Hello. Srinivas sir.